So, hello everyone again. This is lecture 1 part 2 of alternating current. In the previous lecture we have started with the introduction and then we move on to AC voltage supplied to a resistor. Let us move on with the further discussion regarding that concept only and then we can move forward with AC voltage when supplied to a capacitor or an inductor. So, this is lecture 1 part 2 of alternating current. I am Sameer Lavankar. Let us begin our discussion. So, the course outline for you, currently we are on the second topic, that is AC voltage applied to a resistor, and after this concept we will move on to the representation of AC current and voltages by rotating vector. So, basically we will understand a new concept called as phasor diagrams and then we can directly implement that concept in inductor, capacitor, LCR circuit and so on. Okay. So, introduction is being done, we have understood basically the agenda behind this alternating current, why it is necessary, what was the basic difference regarding AC voltage and DC voltage, why it is advantageous to use AC voltage over DC voltage for appliances and so on. So, that thing being said, let us move on with the discussion which we left in the last lecture, that is AC voltage applied to a resistor. So, these all things were explained to you. We understood the formula for I, that is I is equal to Im sin omega t, where Im is nothing but equal to Vm by R. And also we understood that the average current is 0, but the average dissipation of electrical energy or basically the dissipation of electrical energy is not 0. Okay. So, now let us try to understand the instantaneous power dissipated. Okay. So, instantaneous power dissipated is nothing but equal to let me denote that value by P. So, that value P is nothing but equal to I square R. Okay. So, this is the basic formula which we learnt in our current electricity chapter. Here the value of I is nothing but equal to Im sin square omega t. So, Im sin omega t. So, let me just substitute that value. So, it is Im sin omega t whole square R, which gives you the value as nothing but equal to Im square R sin square omega t. Sin square omega t. Now, so this is the instantaneous power dissipated in the circuit, that is P is equal to Im square R sin square omega t. Now, let us try to calculate the value of average value of P over a cycle. Okay. So, average value of P over a cycle is okay. So, basically the denotation of average value is P bar, which is also equal to, so this is the denotation, this may be new for you, that is like this. Okay. What is its value? So, let me just first write the complete value here. So, it is Im square R sin square omega t. As Im square and R are constant, we can take it out of this omega t. Okay. Now, first of all let me try to make you understand basically what is this sign. So, anything which is written on this sign is nothing but it denotes the average of the quantity inside the bracket. So, it basically denotes average of the quantity inside the bracket. Second thing is how it is calculated. So, it is basically calculated in some sort of this sequence, as in let us suppose I write something as, let us say I write something as f of t, where capital F is a function of time t. So, we can write this as nothing but equal to 1 by t integral 0 to t f of t dt. Okay. So, I hope the concept of this bracket is basically explained or clear to you. Okay. Now, let us try to do the same thing for here. So, first of all we know that let us try to ease out the sin square omega t. So, using trigonometric identities we know that sin square omega t is nothing but equal to 1 by 2 into 1 minus cos 2 omega t. Okay, simple trigonometric equation. Now average of this, so basically sin square omega t averaged out for the whole time is nothing but equal to, so as the constants only for an average, so it is nothing but equal to cos 2 omega t. Okay. And next, so basically if we calculate the value of this, we will understand, or basically we will get the complete answer for average value of p over a cycle. Okay. So now let us look at the simple sinusoidal waveform of cos square omega t or sin omega t. So let me first explain you for sine. So basically what happens for sine, if we try to calculate the value of average, what is the value of complete average here? So basically for the complete time sequence, what we are trying to do, we are trying to integrate it. So basically addition of this plus addition of this, what will be the sequence here? This will be nothing but equal to 0, and the same thing also happens for cos. So also same for cos. So it does not depend that it is t or 2t or 3t. So for all, so basically let me just write one more star mark here, that is sin nt and cos nt over its particular time difference is nothing but equal to 0. Hence this value is 0, and therefore what we get is, we get this is nothing but equal to 1 by 2. Okay. So using this sequence here, we will finally obtain that what is p bar? P bar is nothing but equal to, in brackets, I square r, which is nothing but equal to I m square r by 2. Fine. So this is nothing but the formula obtained for your average value of p over a cycle. Okay. Okay. Moving forward, so now what all things can be understood from this sequence? First of all, this is the diagram being obtained here. There is a new concept. So let me first explain it here and then I will write there. So first of all, to express AC power, in the same form as DC power. Okay. So basically we use a special sequence which is called as, or a special value is being designated there, that is called as root mean square. So it is root mean square value, or in short it is also called as RMS. Okay. So the RMS value is denoted by, so denotation is done as I RMS, or in this sequence or in this diagram it is denoted by capital I. Okay. How to calculate this value? This value is calculated as follows. So basically capital I, as the name suggests, root mean square. So we will do a root and we square the value inside. Okay. So this is nothing but equal to half Im square, which is nothing but equal to Im by root 2. Okay. Root mean square value. So root mean, so that is why we divide it by 2, and when you calculate it outwards, it is nothing but Im by root 2. Therefore finally what we obtain is that the root mean square value, or a form of value so as to express this value as a DC current. So what happens is, let us suppose we have an alternating current which has some value with an amplitude of I. We want to convert it into a DC power, or we need to convert it into a DC source. This time the value which should be implemented or which should be given output by a DC source should be equal to the RMS value. Therefore we need a source which is equal. So to make an equivalent DC source, we need the current to pass which is equal to capital I, or which is nothing but Im by root 2. That is the basic concept of root mean square value. Okay. So what is capital I? Capital I is nothing but equal to 0. So 1 by root 2 is nothing but equal to 0.000 707 IM. Okay. So, that thing being said, now let me just write again average power value. So, average power is basically denoted by capital P, which is equal to half IM square R. So, this thing is already being calculated here. So, this is nothing but IM square R by 2. So, therefore, we get power is equal to nothing but half IM square R, can also be written as nothing but equal to I square R. Okay. So, that is how we can directly relate. So, basically in the current electricity chapter we have understood that. So, everything the basic concept which we studied in current electricity chapter was based upon DC voltages. So, there we understood that what is power? Power is nothing but equal to I square R. So, you can see clearly how can we relate AC voltage with the DC voltage. Okay. So, next thing is similarly we define the RMS voltage or effective voltage by. So, let us now define RMS voltage also. So, RMS voltage. So, RMS voltage is as capital I. So, we denote it by capital V. This capital V is nothing but equal to V m by root 2, which is nothing but again 0.707 Vm. So, this is how we define this RMS voltage. Okay. Now, using all these sequences, what we finally obtain is that Vm is nothing but equal to IMR. Okay. Or in another sequence, let us divide both sides by root 2. What we will get? We will get Vm by root 2 is nothing but equal to Im by root 2 into R, right. What is Vm by root 2? Vm by root 2 we just obtained is RMS voltage, and what is Im by root 2? Im by root 2 we just obtained was RMS current. So, therefore, we can directly write capital V is nothing but equal to capital I into capital R. This is nothing but normal value of resistor or capital V is equal to IR, where this capital. So, basically this is how we denote, we can directly relate, or basically how we can relate. So, this is for your DC voltage only, this is for your DC voltage only, but this is for your AC voltage. So, that is how we can understand how we can relate AC voltage with a DC voltage. Okay. So, I think that was only to be understood here. Okay, fine. So, final thing is that we obtained a new concept which is basically called as RMS, root mean square. So, basically we understood current and voltage. What is the value of capital I here? Capital I is nothing but Im by root 2, and similarly what is capital V here? Capital V is nothing but equal to Vm by root 2. This is only and only valid in our sequence till now, that is for AC voltage applied to a resistor. Okay, fine. So, these were the new concepts, I think, and one thing more, that the power obtained or the average power value came out to be equal to Im square R by 2. Okay, fine. So, let us start the further discussions then. So, last equation gives the relation between the AC current and the AC voltage and is similar to that in the DC case, because capital V is equal to IR came in the sequence, which is similar. This shows the advantage of introducing the concept of RMS value. So, that is how we can understand how we can relate basically AC voltage with a DC voltage or AC current with a DC current. In terms of RMS values, the equation for power and relation between current and voltage in AC circuits are essentially the same as those for the DC case. So, this formula came out to be same, only there was a multiplying factor being obtained for AC voltages. So, it was basically if we divide Vm by root 2 and Im by root 2, we will get the values for DC voltage. So, it is customary to measure and specify RMS values for AC quantities. So, now let us try to understand one of the examples here in this line. For example, the household line voltage of 220 volts is a RMS value with a peak voltage of Vm. So, what does it mean? 220 volt is basically a denotation which we try to explain it as a DC kind of criteria, but what is its actual value? Its actual value is root V, that is 311 volts. So, basically what is happening here, from the supply lines this kind of voltage is being coming, which is having some value of amplitude. We are denoting this by Vm. This Vm value is actually 311 volts, but when we try to explain it using a DC voltage kind of criteria, we try to say that actual value of RMS is nothing but equal to 200 volts. So, this is basically RMS value. So, basically we say that in our homes general everything is being supplied using 220 main volt supply line. So, 200 volts or 220 volt which we say is generally your RMS value. Actual value of the amplitude is basically 311 volts. Okay. So, that was one of the explanation. So, in fact, the I or RMS current is the equivalent DC current that would produce the same average power loss as the alternating current. So, this is the main relation between how we can relate AC voltage or AC type of source current and DC type of source current. So, the average power loss. So, basically let us say there are two different devices. If there are two different devices, so what we generally say is that in AC voltage there will be some power loss and in DC voltage there will be some power loss. If you try to implement the current passing through the DC voltage capital I and this AC voltage as IM, then the average power loss in both these case scenarios will be same, and that is how we can directly relate AC circuits with DC circuits. Fine. That thing being said, next thing is above power equation can also be written as capital P is equal to V square by R, which is equal to IV. Okay. So, this is nothing but same power equation which we understood in the previous case scenario, which is equal to IV. So, please remember here capital I, all these things are capital values. So, basically these are RMS values. Okay. So, that was I think the complete explanation regarding all these concepts. So, let me just do a quick revision. So, basically what are all the things we understood? The first thing which we understood was that let us suppose that the current passing or the voltage in this case scenario is capital small v, which is equal to Vm sin omega t, and this led to current which is nothing but equal to Im sin omega t. The next concept which we understood was that the total instantaneous current in a particular cycle is always equal to 0, but that does not mean that the energy dissipation in this complete circuit is equal to 0. The energy dissipation exists. Why it exists? Because the formula for energy dissipation using Joule's heating is basically I square R. So, even if the value of current is in negative cycle, because it is squared upon, therefore, everything will be added up because everything will be positive. Hence, the energy dissipation is not 0. However, the current is the complete current or the average of the current in a particular cycle can be 0. Next concept which we studied about was power. So, in power basically we understood that the complete average power in one cycle is equal to Im square R by 2. To relate it with DC voltage supply, what we say, we understood a new concept which is nothing but also called as RMS value. So, what was basically RMS value? We understood, denoted it by capital I. So, this capital I is nothing but equal to Im by root 2, Im by root 2, and capital V is nothing but equal to Vm by root 2. Okay. Next thing is what is the use of this RMS value? RMS value is basically used upon to link a AC circuit with a DC circuit. So, one of the example which I already explained, let us suppose this is one of the AC circuit and let us suppose this is one of the DC circuit. So, basically if the current passing through this AC is Im and the current passing through the DC circuit is capital I, then the average power loss will be same in both these case scenarios. That is how we can relate your AC circuits with DC circuits. So, that was all the explanation we need till this point for AC voltages passing through a resistor. Now, in the let me stop the discussion here only. In the next class, we will start with this small example so as to understand the concept of RMS, IM, VM, etc., and then we can move forward with the new concept of basically phasors. So, that thing being said, let me stop the discussion here only. Thank you so much.